Okay, and of course nitrate is a polyatomic ion running around those 4 atoms with a -1 charge. Now, one of the things I want to point out is that when any 1 unit of calcium nitrate breaks apart, check out, you just get 1 calcium and you get 2 nitrates. Okay, so that's kind of the stoichiometry of this dissolving process. I mentioned that as what it has to do with solution concentration is this. Let's just say you're going with calcium nitrate, you're going to dissolve it in water, and it's going to split apart into 1 calcium, 2 nitrates. And you could be faced with this question, and this is actually one of your homework questions for Friday. If you know that your salt is 0.230 molar, by the way, the word salt is just a generic term for an ionic compound. Remember, we know it's ionic because calcium is a metal. If that dissolves up, you might be faced with, this is, what concentration is your nitrate ion? Does it seem like you get twice as much? That'll be twice as concentrated as the salt it came from because it splits apart and forms 2? That is true. And I'm going to show you how we're going to do that factor label. But the answer is 0.460 molar, bottom line. Okay, does that make sense? But if we were going to do it factor label, here's what it would look like. We'd start with the molarity of the unionized, or the salt together, with a cation and the anion. So 0.230 moles of CaNO3 quantity 2 per liter of solution. And then it's kind of, I guess, like a regular old stoichiometric calculation. If we want moles of calcium nitrate, CaNO3 2 to cancel, and we want to be left with moles of NO3. Okay, and I've done this before. Okay, what numbers go there for this ratio?
2/1.
A 2/1. Yep, 2 comes from here, and a 1 comes from here. Exactly. What's that?
Did we do these before?
It's kind of like a stoichiometric calculation, kind of like using a ratio from the balanced equation. So, yeah, kind of. Okay, so, yep. Okay. So then if you go ahead and do it that way, your moles of calcium nitrate, CaNO3, will cancel. You're left with moles, units of moles of nitrate per liter of solution, which is molarity. Okay. So of course, and your number is 2 times 0.230, which gives you that 0.460 that we kind of intuitively thought it should be. A lot of times with problems in science, physical science, does that make sense? And you're like, yeah, it makes sense. So now you have a homework problem. Let's take a look at what that looks like. This will be due on Fabulous Friday. Okay, and it looks like this. We have 3 different compounds. I call them salts because they're ionic compounds. Sodium's a metal, potassium's a metal, rubidium's a metal. Okay, and we're supposed to come up with the concentration of, once it breaks apart into cation and anion, what are their concentrations. So I went ahead and did the first one kind of for you. Okay. The Na2SO4 means we're going to get 2 Na pluses and 1 SO4 2 minus. Of course, this is called sulfate, right? Talked about that in Unit 3. And we know that sodium's a +1 charge, like that. So right off the bat, and I think I say you have to show your work, but right off the bat, we know that this guy is going to be double, 0.24 molar, and this guy is going to be the same, 0.12 molar. Why? Because it breaks apart into 2 for every one and 1 for every one. But you have to show it kind of like I showed you before, so you kind of know what the answer is. So do that for all of those. All right. So way back at the beginning of Part 3, which we started before Thanksgiving, which seems like forever, we kind of took that detour after Thanksgiving on Monday. We said you can say how concentrated the solution is in grams of solute per liter of solution. We said you can say how concentrated solution is in terms of moles of solute per liter of solution. Okay. Of course, that last one's got the fancy name molarity. That's molarity. And the last one I said actually was weight percent. So you can say how concentrated a solution is by saying grams of solute per 100 grams of solution. Grams of solute per 100 grams of solution. How concentrated is it? Of course, I went ahead and instead of saying grams of just any sort of component, that's grams of the thing you dissolved, and instead of saying grams of mixture, I said grams of solution, right? So also notice it says down here that the fact that you don't have any volumes in this weight percent, this is weight percent, grams of solute per 100 grams of solution. That is by definition weight percent. The fact that you don't have any volumes in here to swell or contract with the temperature means that weight percent is independent of temperature, which has its advantages. Okay, so let's do a problem. Oh yeah. So oftentimes in chemistry, you don't just want it expressed in chemistry problems anyway. You want to express the solution concentration multiple ways. So for this problem, we're going to work it in class. It's actually just dissolving a liquid in another liquid, isopropyl alcohol in water. First off, we're going to knock out the molarity, kind of like what we've been doing before. Okay, we have the mass of the isopropyl alcohol. We have the formula. We're going to have to knock out the molar mass of C3H7OH, kind of move that around, divide it by the volume. We can do that. And then secondly, we're going to knock out a weight percent of isopropyl alcohol in this water mixture. So I went ahead and posted 2 and 3 together. In order to work that last problem, we're going to need the density of the solution. So actually down here, this says what else do you need to come up with the weight percent of isopropyl alcohol in this solution. The last thing is the density of the solution. So I'm going to show you how we're going to use that 0.975 grams per milliliter to get to the weight percent. All right. So first off, what's the molarity? So we were given the grams and we were given the volume it was dissolved into, but we need the molar mass of isopropyl. It's funny, now remember your solutes don't have to be a solid. This is a liquid solute. So the molar mass, we take 3 times the decimal number for carbon, 3 times 12.01, plus 8 times the decimal number of hydrogen, kind of grouping our hydrogens together here, 1.008. Plus 1 times the decimal number for oxygen, which is 16.00. Add it all together, we get the molar mass, grams per mole of that thing, of the solute, is 60.09 grams per mole. So this is a good place to kind of mention on your test on Thursday, a week from Thursday, and on your comprehensive final, remember you always have to show this work. Most of you are doing pretty good, but some of you are not showing the molar mass calculation. When in my instructions for homework or for a test question, when I say show all your work, this is part of your work. It actually you'll lose partial credit. All right, so we're going to use that in our calculation. So, like we've done before, if we simply take the mass of the isopropyl alcohol, that 46.87 grams of C3H7OH, and if we divide it by the solution volume, which was 300 with a decimal after it. Now remember, that decimal is what we call explicit. The reason that decimal is there is to tell you 3 sig figs. So 300 with 3 sig figs milliliters of solution. So what does the next term look like? We're going after moles per liter.
Do we have to go to liters for milliliters?
Yep.
So milliliter on top.
Okay, I think I had that as the third one maybe. So you say milliliter on top. Maybe I do have this next one.
Oh, that's how I
Yeah,
had it.
no, I agree. She said we're going to fix our milliliters. We're going to put 1,000 milliliters on top, 1 liter on the bottom. Very good. And the second term, and you don't have to do them in this order, for sure. But the middle term is the molar mass of the isopropyl alcohol. So, and we need to use the flipped version of the molar mass. Now, some of you, I noticed on your homework that I gave back, are not including your units all the time. And you always have to include your units. Whether you need them to get the right answer or not, you have to include them. So the units of molar mass are grams per mole. So this is your molar mass. So how many significant figures? 3. I'm liking it. Okay. So I got 0.260. Now if you want to put 2.60. I got 2.60. If you want to put 2.60 m, you can at this point. Or you can put moles of C3H7OH per liter of solution, the same diff. Very good. So that was the first of 2 ways to express how concentrated this solution is with regard to the C3H7OH. So the other one is grams of that stuff per 100 grams of solution. Okay, now, in order to do that, we need to know the mass of the solution. One of the things we talked about before is if you know the volume of the solution, which we do, it's just 300 milliliters, we can use the density of the solution to get to grams, and that's exactly how we're going to use that density. So we're going to use and I'll go ahead and unpack this. Sometimes working these sort of problems, I'll say we, not just students, don't get this right. So when you're given the density, that's the density of the whole thing. That's the isopropyl, that alcohol that's dissolved in water. So the 0.975 is grams of solution per milliliter of solution. That's what that means. Because remember, we kind of unpack things. So with that in mind then, here we go. We go ahead and start like we did before. Go back to the information that was given in the problem. We were given 46.87 grams of solute, 46.87 grams of C3H7OH, and we were given the volume of the solution, 300 milliliters of solution. Now, for weight percent, my target is to get to, just kind of remind you what weight percent is. Weight percent, all I need is grams of C3H7OH per grams of solution. Okay? And then I need to multiply it by 100%. That's what I need to do. So if I then take my density and insert it, so I want milliliters to cancel. Does this make sense that I need to flip it? Flip my density? If I flip my density, then I have 1 milliliter of solution on top, and I have that 0.975 grams of solution on the bottom. Now my milliliters of solution have canceled from my 300 from my density. And now I have units of grams of C3H7OH per grams of solution, which is wonderful. And if I stop right here, which my slides do, so what, 3 significant figures, what you'll get is a value of 0.160. That's what value you'll get. And I think way back when we talked actually about weight percent, we also talked about weight percent, and we talked about mass fraction. This actually is what we call a mass fraction. The mass fraction and weight percent differ by a factor of 100. So we're not quite done to weight percent. In order to get to weight percent, then we need to take that 0.160 grams of C3H7OH per gram of solution and multiply it by 100 parts, or I usually put 100%. Move the decimal place over 2 places. So that gets you to 16.0% by weight of C3H7OH. So it's 2 ways of expressing how concentrated that solution is. but we couldn't do this second part unless we had been given the density of the solution. And notice the second part, we didn't have to use the molar mass. So, all right. So these will also be due on Fabulous Friday. Take a quick look. I wonder if I think I had these. $13. Got my old ones. I may not have this. Oh, I bet it's up here. There it was. Okay. Okay. So the first one is very similar to the problem we just did. The thing that's dissolved is sodium chloride, and you're supposed to come up with how its concentration is in molarity and also weight percent. It's very similar. So I would draw a picture. And here I have the target for molarity is moles per liter. So I kind of remind you of what we just did. I would take the grams that you're given divided by the volume. The volume's already 1.00 liters, so that's kind of nice. Plug in the molar mass to get it to moles per liter. So you should be fine there. And then for the weight percent, I would take well, here I have kind of a separate problem. Instead of putting the liters of solution, wait, I don't know. Is that all the hints I gave? It's very similar to the homework. Kind of tell you what the target is, and you're going to be using the density, the flipped version of the density to get there. Oh, here I did. Oh, yeah. Okay. And then for the last one, it looks like this. Okay, in this case, you were given the weight percent and you're supposed to get to the molarity.
So it's like backwards.
It is kind of backwards. And here I unpack what that weight percent means. 5.88% NaCl means that in 100 grams of the whole solution, you have 5.88 grams of NaCl. So then, and your target is molarity, which is moles, not grams of NaCl. In the bottom, you want liters of solution, not grams of solution. I would start with that as my first term, and then I would stick in the molar mass to fix my get to moles, and then I would stick in the density term to get to liters down here. Actually, it'd be milliliters, then you'll need one more term to fix the milliliters. So that's my hints, and I'll put these out there on Twitter. That kind of walks you through it.
I like the
Good. You like to tweet? Oh, is there one more page? Okay, actually it's blank. That's good. Okay. So one more thing I want to talk about this morning with regard to solutions. You're like, really? Could there be anything else? And yes. Sometimes you need something that's just a smidgen, very dilute, very, very dilute, okay? And the best way to get it very, very dilute is not to go straight for that concentration. It's basically to make something that's kind of concentrated, take some of that and dilute it up, and then take some of that and dilute it up. It's much more accurate, okay? The problem comes in when you're trying to just like let's say you're dissolving a solid, and you need, here you need like, 10 grams, and here you need like 0.0001 grams, okay? So it's really hard to weigh up 0.0001 grams, but you can weigh up to 10 grams and kind of serially dilute it, okay? So this is kind of what that looks like. So all the equipment you need is here in this first picture, kind of going from left to right. The nice dark colored solution here actually is potassium dichromate. The concentration is 0.100 moles per liter. Okay, we've got and these are volumetric flasks. You guys don't use them, but I use them a little bit in the chemistry lab to make up solutions. And they actually have just one calibration mark. Here's the calibration mark here, and I don't know if you can kind of see the calibration mark right there. So they actually only contain one amount. This one contains, maybe that might be 100 mils, I'm guessing. And this one is 500 mils, so it's probably 500.00 mils, is what it contains there. So we're going to go ahead, and the first thing we're going to do is take this other device over here. This piece of glassware is a pipette. Remember, we don't suck liquids up in a pipette. Actually, this hand over here used a pipette bulb and went ahead and sucked up to the line this solution. Now, this is what we call the stock solution. That's what you start with. Okay. And then they are going to transfer it into the empty flask. So here it is being transferred into the empty flask. Once it's all transferred, then the last step is to go ahead, and that's why this water bottle's here, go ahead and bring it up to volume. So how can you tell that the second one's more diluted?
It's more clear.
Yep, it's lighter. And it's possible that in a serial dilution, go ahead and take some of that, transfer some of that to another volumetric flask and keep diluting it down. This actually, let's see, how do I say this? This was a 100-fold dilution. I know it's a 100-fold because we took 5 milliliters, and we diluted it up to 500 milliliters. Okay, that's a 100-fold dilution. And actually, we can kind of see that in the molarity. This one was 0.1 molar, and this one was 0.001 molar with 3 sig figs. Okay, so a couple trailing zeros after the 1. All right. So the problems we need to do next is actually to do the calculations to see what the concentrations are going to be. So that's where the problem comes in. So switching it up from potassium dichromate to potassium chloride, let's just say somebody assigns you to go to the lab and they need 5 liters of 1.50 molar potassium chloride. And they have a stock that's 12.0 molar. How would you do that? Okay. Well, after doing some ciphering, okay, you would figure out, and this is, we're going to do these problems, you would figure out that you needed a quantity of 0.625 liters of your stock, okay, and you would add it to your 500 milliliters. That's the problems we're going to be working with. Then you would dilute it up. And I think I've mentioned this before. Don't, I laugh because it's not really funny, but if this is your final solution you're ready to give to somebody to use, don't forget to mix it one last time, unless you want to set them up for failure. Okay, if you don't mix it, depending upon mobility of your solute, it's going to be concentrated down here and diluted up here, dilute up there. So, all right. So what do you guys need to know? How does the dilution problems look? I think I'm going to go ahead and write this on the board. I really like pictures for these problems. I like pictures for a lot of chemistry problems. Okay. So it says 25.0 milliliters of a 0.160 molar calcium chloride solution is pipetted. So now this is this. Okay. We have a concentrated solution over here on the left. So we'll call that the stock. Okay. And it's saying 25.0 milliliters And over here with the stock, I go ahead and say what it is. 0.160 molar calcium chloride. Okay, is pipetted into another volumetric flask. I know my volumetric flasks look terrible, but the volumetric flask has a capacity of 125, bless you, milliliters. Okay, so this is going to be my diluted. So if you just kind of think of it as it's going to happen, okay? And then it says after the transfer happened, they went ahead and diluted this up to volume. So the question here, if I'm going to put it anywhere, is going to be question mark, what is the molarity of my diluted solution? Well, I think it works pretty well to break up the problem. We're going to do a first problem, and our first problem is going to involve the transfer volume and the, and the molarity of the stock, okay? If we can use this volume and this molarity to, like this says, get to the moles that we put in here, the moles specifically of, what was it, calcium chloride. So that's step one. Once we have the moles that are here, the second part of the problem is simply to go ahead and take those moles and divide by that volume to get molarity. That's it. That's totally it. So the second part is to take the moles that were transferred. So 1 moles transferred, 2 molarity of diluted solution by taking moles transferred divided by solution volume. That's it. Totally it. Okay, so the thing, like this slide says, that connects kind of the, bless you, kind of the two parts is the moles of the calcium chloride that were transferred. That's it. So here we go. And sometimes when I'm working on, I like actually give my parts of my problem a title, because I'm like, dude, if I have to go back and scramble for, well, I have to do something different with my problem, at least I've labeled what I've done so I don't have to reinvent the wheel. So moles of calcium chloride that was transferred. So this is the first one, moles transferred. So we need to take this volume, I'll put it over 1, and then I'm going to use molarity to get to moles. But this is kind of like what Becky said. The first thing is I got to go ahead and get my milliliters to liters, right? So I'm going to put 25.0 milliliters solution over 1. How do we get that to liters?
1,000 milliliters on top.
Not on top.
I mean on bottom.
Yep, 1,000 milliliters on the bottom. 1 liter over 1,000 milliliters. Very good. Now, how do I use the 0.160 to my advantage? Got to be a ratio.
It would be liters on bottom, 0.16 moles on top.
Yep, 0.160 moles on top. Very good. And liters on the bottom. Now, I've gone ahead and said what the solute was, calcium chloride, but you wouldn't have to say that because we're just dealing with one species of anything here. But now the cool thing about all that is milliliters cancel, liters of solution cancel, and we're left with moles, which is exactly what we were after. So how do we need to round this?
3 sig.
Yep, I'm liking 3 sig figs. So we have some trailing zeros after the decimal to give us our 3 sig figs. So 0.00400 moles of calcium chloride.
Wait a second. Okay, so the last 2 zeros, they don't count, but the first 2 zeros before the decimal point count, right?
The trailing zeros after the decimal are right. They're not right after the decimal. These are after the decimal. These are the trailing zeros. Yeah.
Okay.
I guess if I emphasize the word trailing, the trailing zeros after the decimal. Yep. So those count. These guys don't count.
But they're still important.
They're still important. Yes. Don't blow them off. So now we're ready for part 2, which is to take those moles and divide it by your dilution volume. So we take the 0.00400 moles, CaCl2, and divide it by 125.0 milliliters. Now, will that give us molarity? Not quite. What else do we need to do?
Milliliters to liters.
Yep, milliliters to liters. And how we do that?
Milliliters on top.
That I buy, milliliters on top. So now we have moles of calcium chloride per liter of solution. Perfect. 3 sig figs, because 125.0 has 4, but we have to go conservative, so 3. Okay. So I get 0.0320 m CaCl2, or 0.0320 moles of CaCl2 per liter of solution. That's it. The problem with chemistry problems is sometimes they take like little variations. So I'm not a fan of memorizing algorithms because I'm like, ugh. About the time you think that works, then you come up with a different problem. So here's another dilution problem. I did bring my coffee. Okay. All right, so how many milliliters of 0.135 molar NaCl? So I'm going to put 0.135 molar NaCl on my left here. That's actually my stock. If you read this a few times, and I had the opportunity to read at my desk before coming today. So this is saying my stock has a concentration of 1.35 molar. The analyte or the solute is NaCl. And it goes ahead and it says how many milliliters. So I'm going to put my arrow, I'll put question mark mLs. That's how I get from that first part of that sentence. Okay? How many milliliters of 1.35 molar NaCl must you use to prepare a 500 milliliter? So over here, to prepare means that's my diluted thing. Goodness, my flats are terrible. Okay? So my capacity is 500 milliliters, okay? And over here, I want this concentration to be 0.275 molar NaCl. Okay? Now this one's different because we don't have the volume, so we really can't go for the transfer moles right away. But what we know enough about is this over here. So actually, the first step here is going to get to the moles of NaCl in diluted solution. We can do that because we have molarity and volume. We can do that, the moles. Okay? And those moles, those cute little moles of NaCl that are swimming around here, came from that. We use the word aliquot. I just love that. Like a little volume, that's an aliquot, transfer aliquot. So once we have those moles, our second step is to take those moles. Let's see, how does that work? Oh yeah. We're going to take those moles and the molarity of the stock to get to volume. That's it. A little less obvious. I'll show you how that works. Okay. So again, what's connecting? It's the solute, the NaCl. What do we know about the NaCl? Well, we know how much NaCl we have over here in our diluted solution. So we're going to get the moles that are there in total, okay? And then we're going to use those moles with the molarity of the stock to get to volume of the stock. Bottom line. And on Friday, we're going to do one more type of calculation that uses this technique of getting to volume from molarity and moles. Okay, so here we go. Starting with the diluted. What are the moles of NaCl over there? Well, you can do it a few different ways. I'm going to go ahead and start with the volume. I'm going to fix my volume to liters. So 500 3 sig figs milliliters solution. So my next term is going to be the 1 liter over 1,000 milliliters. Then I'm ready to insert the concentration of the diluted solution. And I want liters to cancel, so do I flip it or use the non-flipped version of the molarity?
Non-flipped.
Non-flipped, 0.275 moles per 1 liter, exactly. 0.275 moles of calcium chloride per 1 liter of solution. Now, fortunately, milliliters have canceled, liters now have canceled, we're left with moles, which is what we wanted to know. So it looks like 3 significant figures, and I get 0.138 moles of NaCl came from that transfer aliquot, the unknown milliliters. But what is known is the molarity of the stock that they came from. So now in the next part, this is going to be my first term, 0.138 moles of NaCl. So if that's my first term, how can I use now the molarity that those moles came from to get volume? What does that look like?
Do we have to do the molar mass at all?
No. Here's your hint is this guy, remember anytime you see an M, that means 1.35 moles of NaCl per 1 liter of solution. So how can I use this to get to liters to get to volume?
1 liter on top and 1.35 mils on the bottom.
Yep, exactly. Was that what you were going to say, Jeremy?
Yeah.
Mm-hmm. You put 1 liter of solution, this is from molarity, 1 liter of solution over 1.35 moles of NaCl. I'm almost there. Whew. So how can I get from liters to milliliters?
Oh, liters on bottom.
Liters on the bottom. 1,000 milliliters over 1 liter.
I got that part down.
Okay, so this will give us the volume that I transferred from my stock in order to have those moles show up over here in my diluted solution. 3 significant figures. I get 102 milliliters. Seems like a weird chemistry number. So those are dilution problems. And there's, I'll try to post them on the website, on the homepage, but there's all sorts of like apps, like for your smartphones and stuff, and like little programs out there on the internet where you can just kind of plop in the concentrations and knock out, in this case, volume, or in that case, knock out the molarity, given what information you need. So that brings me to this point. So you're going to be tempted, especially if you've had chemistry in high school, you're going to be tempted to use this kind of awesome shortcut. I say it's awesome, and then I say you can't use it here, right now. And the ones in the 2 subscripts are referring to the stock and the dilute. So basically, and you can use it to check if you want to, but what they're saying, and you can check it with these if you want to, if you were to take the volume and the molarity of the stock, bless you, that would be equal to the volume and the molarity of the dilute. If you look at it this way, with our dilute, what happened? Well, our constant molarity went down, but our volume went up. And that's always gonna be the case. So it's kind of a nice way to check, but alas, you cannot use it. So this, if I'm counting right, is the third set of homework that's due.
Yeah.
Yep, I am. On Fabulous Friday. And, let's see, I think I'm gonna have to try to pull this one.
Did you stuff that we did, like our homework that we did that day?
This would be
You understood it?
81, 85.
Oh, did you? That's as far as I got. I did the.
They're pretty easy, they're all in the same size.
Ah,
I did the last three, just like the first three.
Just like the other centerpiece.
I think it's because I keep like separating them.
Look at that shape.
Not separating them. Yeah,
Just like
check it.
no, I'm drawing a blank for these. Let me check one more time. 91. This kind of looks like it. Mm.
Oh my gosh, I got the first thing right. I think I make them harder
Sigh.
than they are.
Okay, nope, I can't find those. But I'll take a minute, I'll kind of wrap them up and push them out there on Twitter too. Okay, so that's all I have today.